Dr. Fitz here on Space and Time. We're going to look at Lorentz contraction and time dilation. Here we have our two reference frames, inertial frames, K and K prime. Remember, K is our laboratory frame. K prime is moving down to the right here, x-axis, along the x-axis, that's speed v. And we're going to place a rod in the moving frame, and we're going to call that L sub 0 because that is the length of the rod in its own frame. And that's called the proper length of the rod, the proper length. And then we're going to see what we measure in the laboratory frame as we watch this L naught zip by at speed v. Well, we start with our Lorentz transformation. We have x prime, is x minus vt, the Galilean transformation, divided by the square root of the 1 minus v squared over c squared, and we take deltas. Delta x prime is equal to delta x minus v delta t. Now, delta x prime is going to be the length of the rod in the frame in which the rod is. So that is L naught. And delta x, what I measure, is going to be what I get for L in the laboratory frame as I watch it move. Notice that when you take this measurement, you need to nail both ends at the same time. So delta t must be 0. Otherwise, if you say, hey, I'm going to measure, here's the length, this is measured by, here's the left part of the car, and then I wait and get the right part of the car, then I'm going to get a false value. So I have to measure the left and the right part of a car or a ruler or anything at the same time. So when I do that, I then get delta t is 0, and I get L naught, the proper length, is L is measured by me in the laboratory, divided by this, and I like to write down what I get. So here is L. I measure L is the original or the proper length of the rod, and it's contracted because as one is moving with some speed here, this is going to subtract from 1, and I'm going to see a contraction. This is called Lorentz contraction. For time dilation, what we do is we put a clock. Let's go ahead with this set of equations, so we'll talk about it here. We put a clock in the moving frame, and as the clock is put in that moving frame, the clock has the proper time for the time that it reads in its own frame. So just think of your proper time as always being the time that the watch reads in your pocket, because you're with the watch. All right. So what I want to do here is I want to have the clock not move. So I want to look at these three parameters. I want to look at delta t prime, which is the time of the clock in the moving frame, the delta t that I measure, and I want to make sure the clock doesn't move in its frame. So I need delta x prime. So these are the three key deltas I need. The time increment of the clock in its own frame, the time increment of the clock in my frame, watching the clock move by, and to make sure the clock in its own frame, the K prime frame, doesn't move around in the K prime frame. So the clock has to stay put. So delta x prime is going to be 0. So I need an equation that has delta x prime, delta t prime, and delta t. So I need an equation that has x prime, t prime, and t. Well, the Lorentz transformation doesn't have that. I don't have t prime and x prime and a t. I have just one t prime, and then I have t and x, or I have x prime and x and t. So I have two regulars, so to speak, and one prime, two regulars and one prime. Well, I need two primes and one regular. So what I do is the inverse transformation. In other words, I'm going to write x and t in terms of the primes. Now you can solve this equation, these equations, and derive this and take a long time and do a lot of algebra and maybe fill up a page, or you can do it in 1 second and write the answer down. What you do is you let v become negative v and swap the primes with the unprimes. In other words, we're saying, hey, if I'm on the K prime frame, then I'm going to watch you in the laboratory moving the other way. So see, we're doing a switch here. So that's a very elegant way of getting the answers. So this x prime becomes x, and these become prime, and a plus sign for the v, and this is the inverse transformation. We simply switch prime and unprime and make v become minus v. So now I have the equation to look at, and that would be the x prime, t prime, I get x prime, t prime, and t. So I use this equation. So using that equation, I then set up delta t prime, and delta x prime, and I make sure that this is 0 because the clock cannot move in its reference frame. Delta x prime must be 0. It's neat though, if it did move, look, it affects the time that I measure. But I want to measure the property of the clock, you see, having everything else out of the way. So this really needs to be 0 so that I can get a true measurement of just the clock time itself. So that goes away, I get 0. And the t that I measure is t, and the time of the clock in its own frame, the t prime frame, is by definition the proper time. And when we look at this, we see that the time is dilated, which we mean longer, because when you divide by a number that's smaller than 1, you get something bigger. So here is our summary of Lorentz contraction and time dilation, and this means, yes, I will experience a longer time. So when you eat your breakfast on that rocket ship going very, very fast, and you eat your breakfast in 15 minutes, for me it might be 4 hours. And this leads to very interesting results, like if this person here is traveling very, very fast and comes back and returns, I will be much older. And if I had a twin that did this, my twin going very fast, coming back, would not age as much as I would age. And that's a neat effect. Actually found to be true experimentally in the 1970s with atomic clocks on airplanes. Wonderful result, and very, very important in global positioning of satellites and the clocks that are in orbit around the Earth. These effects need to be taken into consideration. Marvelous stuff that has engineering applications today.